Yep. I'm talking about those two projects in the Apache Foundation. One of them is quite new, which is Arrow, and the other one, Parquet, which is a lot older, but both of them are quite new to the Python ecosystem. And I want to talk a bit how you can use them and how they can help you to integrate other systems which are not Python into your process. A little bit about me. I'm a data scientist at Yonder. We're a company dealing with retail optimization problems like replenishment. We have some kind of big customers with a lot of data, so we need to take care of this data and ship it around, do computations on it, and pass it to different systems. In my daily work, I'm mainly focused on Python, C++, 11, and SQL. That's like for all of my colleagues. So it's kind of important if we integrate another system that we can interact with the system with these languages and don't have to learn another language because then you have to maybe train the whole company in Scala, additionally to all those 4 languages already. In my talk, I'm first going to state the problem. Why do we need Arrow or Parquet? Then I'm going to show about how Parquet and Arrow solves this problem and give a short outlook what those 2 projects are going to see in the next time as features or releases. The first important part, which I'm always going to reference in this talk, is columnar data. So if you don't know why we need columnar data, a short introduction to it. In a typical data science problems, you have this kind of table where you have rows and columns, and your columns are named. And in each column, every entry is of the same type, like having integer or date. And because we're using computers which can't access 2D memory, but have a linear memory, we need to have a representation of our data linearly in memory. And for the typical workload in data science, you normally make an operation on one column, like an aggregate or a scan. And therefore, we want to optimize how the CPU can access this memory and how we can work on the memory. And columnar form is beneficial here, because if we're just working, for example, on the session ID, we will load a large chunk of that through the memory bus into the CPU. Normally, memory bus loads more than a register, like maybe 64 bytes or even a kilobyte, down directly from memory with single memory latency. And then you have special instructions on the CPU which also can do, like for 4 values or 8 values at a time, one computation. This is called SIMD, single instruction, multiple data. And if you have data in columnar format, you can exploit these and get a significant speed up against this row-wise form where you would download more data, you would do more memory requests for the same amount of interesting data. And this already results like in a 10 times speed up often, because you get rid of so much memory latency and get your CPU throughput much higher. But the actual problem is, nowadays for doing like big data and data science stuff, you have really a lot of systems, a lot of solutions you can use. And typically if you have a problem, there's not one tool that solves it all, but actually a combination of 2 or 3 tools will do the best job. And then you have to take care of how do you combine these tools. Some of the tools are built in Python, some of them have a good Python API, some of them even don't take care of Python yet. So you have to think about how do we stick together and how are we going to write the routines that transfer data from one system to another system. And typically, for each pair of these systems, you write a special routine which takes the data from one system, serializes it, passes over the wire or on disk or on memory, and deserializes in the other system. This involves copying the data and also does a lot of CPU compute time just for data serialization. And to solve this problem, that we can use these tools. All those tools work on columnar data, so they have like the same understanding how the data should be shaped in memory. Recently, there was the in-memory specification Apache Arrow developed. This is a combined effort of people in the JVM world and in the native world to have a common memory format you can use as interchange or even as the basis of your computations for columnar data, so that if you have one tool and want to ship the data to another tool, you can just pass the pointer to the data. And you don't need to have any conversion routines or expensive serialization tasks. And this memory format has also in mind, like I mentioned before, having these SIMD and cache locality, so you can exploit everything your CPU gives you to make your application fast. And it's not about just data frames or tables like I showed at the beginning. It's also have a bit more encoding, so you can have nested data, like if you have kind of JSONs and you want to store 1 million times similar structured JSONs in columnar form. This is also supported by the specification. To even give you a bit background why Arrow is important, I have a real-life example where we don't have Arrow yet, but it would be just the solution if we have then later a release of Arrow and could use it in production. A typical problem we see every day in work is we have data stored in a big database, which has the data stored columnar, can scale out for the query over multiple nodes to get a flat table, which I can then analyze in pandas, make some interactive tools on it, train a model. To get this data, I'm writing a big SQL query, execute it, and then receive it in the database driver in columnar form. The database driver is just adhering to the ODBC standard, and because of that standard, it transforms it into a row-wise form, and then you can use Python dbap2 or so to load it in Python. And because we want it in pandas, we transform the row-wise data again back to pandas. And like you see here, you have multiple copies of the data. You change the format of the data, which is kind of CPU expensive, and also gives you a lot of cache misses, which makes it really, really slow. The current hack we're using to make it fast is actually just to dump it out to CSV, because amazingly CSV is always implemented really, really fast, and that's a kind of cheap API because everyone focuses on making CSV fast, and it works. But that's kind of poor solution because it's fast, but it's still not as fast as it could be. And the correct solution would be that you would take Arrow, implement it in your database, that your final result of a database returns an immutable Arrow result. And then you can, if it's per wire, you can pass it just with some metadata over the wire. Or if it's in the same program, you can pass the shared a pointer from the DB driver to pandas, and then pandas can take this Arrow structure. And then you wouldn't have any serialization or conversion overhead anymore. A general bit about Arrow. Arrow is a top-level project from the Apache Foundation from the beginning. That means it didn't have to go through the incubator and show its importance, but the people who started Arrow already could convince the Apache board that this project is so important that it should skip the incubator and directly be a top-level one. That also comes a bit from that this project was not really started by just 1 or 2 people, but from a lot of major open source projects. These all have to deal with the problem. They have different APIs. They actually want to interact, so they needed a common standard. So they met and just made some basic scaffold, which is now developing, and you already can see online at this link. As I mentioned already, Arrow is a specification how to store columnar data in memory, but additionally to that specification, we already have some code, like how you present these arrays in Java, how you allocate them in Java in an effective way so that it's aligned, and the same thing on the C++ side, where we also allocate those arrays, have builder structures to make these arrays in a kind of dynamic form. There is some people now working on RPC support, so you can pass remotely Arrow arrays, and there's already an alpha implementation for interprocess communication, which uses memory map files. So you can pass from one, like from JVM to C++, one array without copying it. This is a moment using memory map files. In the future, we hope to have an implementation that is using just pointers with reference counting, so you can safely pass the memory from the JVM to native code. Also inside Arrow is conversion routines. So you can load Parquet data into Arrow structure, and so that you can use convert Arrow memory to Pandas memory. There is sadly some copying involved because Pandas, or kind of NumPy, we have some other definitions about how they store null values. NumPy has this mask array which uses bytes, and we use bits in the Arrow. And Pandas just don't use any missing values, but just converts the type to float and uses not a number. And for that, some copying is involved, but if you have a simple integer column, no copying is involved if you go from Arrow to Pandas. And what you also see here, Parquet is a file format, which I'm going to introduce to you later. We have a conversion routine for that into Arrow, and we have a conversion routine from Arrow to Pandas. So at the end, we should get just a Parquet reader for Pandas for free. As mentioned already, Arrow is in an early state. It's developing. It's kind of 4 to 5 months old now, the standard. So it's not really production ready. But there is already a tool which you can use. It's the Pfeffer file format. It's made up from Wes McKinney from the Python side and Hadley Wickham from the R side. It's quite a simple format. It's just take the Arrow arrays, how they are in memory, and push them one after another into a file. And at the end, store a bit of metadata where you say what type this array is and where the array starts and where it ends. This is a good format just if you want to interchange quickly data frames between R and Python, for example. It has the limitations, all of your data has to fit in memory. And it's at the case where you don't care about disk I/O. If your disk is really fast, this is the format for you to use because it won't introduce a lot CPU overhead to load. Like parsing CSV will take a lot of CPU. If you load an Arrow file, you normally don't see any CPU load. So that's one of the first ways how you can use Arrow without actually seeing that there's Arrow inside. So after this short introduction to Arrow, I want to go a bit more detail into Apache Parquet. Apache Parquet is also a file format for storing binary columnar data. So it stores the same stuff like Pfeffer, but it is a bit different from Pfeffer that is not storing the data plainly in every case. Its origin is from a Google Dremel paper, which describes how Google is doing querying on big data. And Parquet has taken some ideas from that, how to store this data efficiently so you can query it and have data sets that are larger than memory and load just parts of it. There's several building blocks so that Parquet can do this. There is first, it has multiple encodings. You can store, if you have each array in a data frame, you can either store it plainly, like how it is presented in memory. You can do bit packing, like if you have booleans, you use for a boolean just 1 bit. Or you can have more complicated things like dictionary encoding, where you have strings, you define every string at the beginning, give it a code. Or have run length encoding for maybe repetitive data, where we say, okay, I have an array, I have 100 times a 1, 2 million times a 2, and you just store the counts and how often it is there, and you maybe can encode a very large column with 1 million values in just 20 bytes just because it's a repetitive. There's something called predicate pushdown, which means that if you do a query on that file, you also could leverage the file or metadata stored in the file to skip data if it does not fit to your query. I will talk a bit more on the next slide how Parquet file is structured. But in each unit of Parquet file, you can store metadata like minimum or maximum. And if you know, okay, I have a query which should work on all the data, but it should only work on the data where column X is higher than 10. And if your unit in the file says, okay, the next 1 million values are less than 10, then you don't have to read them. You can just skip them and go to the next position where you can start reading again, so that you can already accelerate your query execution down to the file reading level. And another thing is Parquet has compression, but that compression is done on a column level. So that if you only need to load one column or two columns, but don't take care about the other 100 columns stored in that file, you only need to decompress this one column. Or you actually only need to compress the columns where compression brings something for you. If you have to like run length encoding, probably compression will not do you any benefit. It just makes the overhead that you have to call the compressor and maybe copy a bit more data. Parquet is a really widely used format. A lot of tools use it as default format. If you like read a Spark tutorial, they also always advise you to use Parquet. Impala uses Parquet as a default in its documentation. But the thing is, it's mainly developed with the Hadoop world in the head. So you see in all the Hadoop tools, you have Impala supporting it, Spark supporting it. Hadoop MapReduce itself also has a really good support for Parquet and for pushing down the queries to the file format. This is mainly due to the lack of a really good native implementation. Impala is in C++, had a native Parquet reader, but didn't have a really good didn't have any write support, and the reader implementation was really private to Impala and not used as a library. Now, very recently, we had some efforts that we now have a native Parquet reader, so you can read Parquet files in CPP, in C++, and load it into memory. And in combination with Arrow, because we have a small wrapper that you can load those Parquet files into Arrow memory, we will hopefully get next time a reader so that you can read Parquet files in pandas or in NumPy arrays. And actually, last week, I committed a pull request where you should already get integer types from a pandas data frame into Parquet file and back again. And that's already working. It's not production ready because we're doing some more copies than we should do. And we didn't do any benchmarking on the Python side if we have there any overhead we have to optimize. But if you're having some fun, you can look in the code, try to compile it, and try to have a look if it's working for you. And now the Parquet format is a bit special in how it is structured. I'm going to give you a short overview how it's done. And that's really a nice thing about Parquet. The specification is quite short. So if you read the full specification, it will be about 4 pages. If you compare that, or maybe 5, leaving out a bit maybe of the encodings, but if you compare that to HDF5, which has about 150 pages of documentation of the specification, it's really simple. The main structure of a Parquet file is normally look at one file. Typical systems iterate over files, so if all files have the same structure, like the same number of columns with the same type, you can just treat them as one file. And per each file, you have stored metadata, which tells you where a column is and how this column is encoded, where the next thing I'm going to play is where the row group starts. Because in Parquet, you have a split up every X rows. So you can say, okay, I make a row group for the first 100 or 100,000 rows where I store the data for those. So if I don't need those and want to skip those, I can just jump in the file to the next 100,000 rows. And each row group has the same number of columns, which is also globally in the file that we have a fixed number of columns. And in these columns, we have separated the columns again into pages. Pages are the lowest unit, but a unit you as a user normally shouldn't see. But you have to know about them that those are the lowest level where you can put statistics and the lowest level where you can decide in your query if you should load this data into memory or not. And this is kind of to the nature of Parquet that you really want to have, that your query engine or your computational task already propagates down to the file format and that you only really load the data you need. So you only specify the columns you need and only load those columns, but you also specify with a predicate which data in these columns you should load. This is so that you minimize really the I/O overhead, because most use cases, your Parquet file is on network drives or like HDFS and not always local to your worker. So you have to minimize like how often you transfer data and how much. Also, this means this pre-partitioning for fast distributed access. And with those pages in a column, you can scan over a column, identify which rows you need, and then if you want to load other columns, you already know which rows in the other columns you have to load and can skip the other ones. There's a bit more to Parquet. It's the handling of the nested structure, because Parquet is supporting, like Arrow, more than nested structures, more than just simple arrays, but nested structures. And it supports null values on each level of those nested structures, which is a bit more you have to learn if you really want to understand the format. But there is a blog post by Julian Ladem, the person who created Parquet some years ago. This nicely explains how this is done. So if you want to dig deeper, you may have a look at this blog post. It also explains a bit more about the file format itself. But the cool thing is we're here in a Python conference, so you actually want to use Parquet in Python. I already said it's not yet possible because there's no native implementation, but actually you already can use it because Spark has a Parquet reader and it has a Pandas API. So you can just load a Parquet file in Spark and pass it to Pandas. But once you try it, you will realize this is not a good idea, because passing data in Spark to Python is currently a bit inefficient, because in the intermediate, it sometimes even converts the array values to native Python objects, which makes it really slow. And for that, upcoming now is that we have this Parquet to Arrow converter, and that we have in Arrow some conversion to NumPy or Pandas routines, and thus you can use those two hopefully next week if I get my pull requests all merged, or in production in the next months, because we're still far away from a release. But then you should be able to use this file format, and you can use the same format as you would use if you're using Spark. And if you have any output of typical Hadoop tools, which you want to inspect, you can now skip the way you have above there, like taking Spark and passing to Pandas. But also, if the computation is over, you can just go to your file system and grab one of those Parquet files and load it into Pandas and make an analysis how this chunk of data looks, what's in there, and use your typical tools without having to go all this way back to a Spark engine. A bit on the state of the projects at the moment. We can split up the state of the projects into languages, because that's roughly where the work is kind of separated. In Arrow, we have currently Java in a beta state, because the Java implementation is a bit older than the specification. It came out of the Apache Drill project. So they're kind of at a stage where it's usable, where it's efficient, and where it's kind of stable. C++ and Python implementations are both in progress. The memory structure is there. Inter-process communication and RPC is not there or in a very alpha state. And Julia and our people are looking at Arrow at the moment. There are some implementations mainly coming out of the Feather project now, because people saw Feather and are now excited about Arrow and trying to implement them in those languages. On the other side, in Parquet, as already mentioned, it's a bit older. So Java already has a mature implementation, or actually has many mature implementations, because different tools made their own implementations and own optimizations. In C++, we're nearly there having a general purpose library. There's still a lot of pieces missing. We can read probably everything which Parquet can write, but we can't write everything what's in the specification. So that is a thing which will come in the next month. And with the C++ implementation, actually directly the Python wrapper and Arrow gets the new features, only for like a different encoding. What we're missing in Python when it's in C++ is just the keyword argument in the function call, and then you directly get the feature. And the nice thing is, because we have a C++ implementation, and we hopefully have Julia and R wrappers in future that are stable in Arrow, we directly get an interface to Julia and R. So that's mainly coming for free. The only thing you need there is the call, how to open the Parquet file, or the function call, how to specify how the Parquet file is written, because you can specify a lot if you want to read a Parquet file and make it optimized. On the feature side, what is coming is already mentioned several times. We're going to have a Parquet pandas reader, so you can use this format natively in pandas. And there's an inter-process communication is currently the other hotspot where development is happening. And hopefully soon we have the shared reference counting between the JVM and native Python code. So you can pass around your arrays without having modifications. Like you have seen in the beginning, like Olivier presented, where you have typically when you have data in Spark, Scala code does some computations, then it takes the data, serializes it, passes it to a Python process, so a different process, unserialize it there, make some Python computations, and serialize it again, passes over to another process and deserialize it. Probably we will not get this down to that we have JVM and Python in the same process, but it would be nice if you could skip the serialization steps and just, if we're using Spark, you just pass on the same data and then with little overhead make those computations in Python so that Python operators in Spark are not awfully slower than ones written in Scala. Those two projects are, depending on how you look at them, quite young or old. Therefore, it's kind of good time to get involved, to shape them, how you think they could help you. And therefore, you could join the mailing list. We have a Slack channel for Arrow and their websites, and you can follow on Twitter. But the most important thing, I think, about Arrow and Parquet is that you look at the code, because on the Python side, there is not so much documentation at the moment, because the efforts are young. They both started in spring 2016. We're hoping to get maybe around autumn to the first releases with some documentation then. But at the moment, the documentation is mainly how the main function calls. And even though Arrow is now hyped and people get excited about it, hopefully in the end users of like Impala or Pandas don't really realize they have Arrow, because Arrow should be the back end of the back end, where people can pass around data, and other people would use this software don't notice that there's a lot of serialization going on, because there is just none. Okay, was a quite bit fast, but now I'm open for questions.